able to. Thank you all for joining today. So today we're going to talk about building a real-time RAG system using open source technology. As said before, I'm Stefan Batifo, developer advocate at Zidiz and Milvus. If you have any question related to Gen AI vector database, LLMs, how to improve anything you're doing with AI agent as well, it is what I work with. So feel free to hit me up. And yes, I'm joined here today by Tune.
Hey folks, thanks for joining. Hope you're enjoying your lunch. My name's Tun Shui. I'm the VP of Data at Quix. Scan the QR code and connect with me on LinkedIn, and we can talk about all things data engineering, building data products, and my favorite subject, which is real-time data systems.
Cool, thank you. So the agenda today, we are going to have a quick introduction about large language models and LLMs. A lot of people talk about them, but not that many people know how they're trained. So this is kind of the idea. You can follow a bit. Then a bit of an intro as well for vector search and vector databases. You know, vector databases have been very popular for the past 2 years now. But I'm just going to tell you a bit how they work, how it works, and how then you can understand a bit better, so you can do better RAG systems. We'll then move on to Retrieval-Augmented Generation, so RAG. We'll have an intro on this one. And then you have a better idea of how it works, at least the basic version. Then we'll move on to the streaming data part, and then real-time RAG, and we'll finish with a demo where we can see actually real-time RAG in action. So let's go. For large language models, what are they? Well, just going to start with an example of, what it consists of. People imagine that large language models are like, things that are very advanced. In the end, it's only weight and 500 lines of code. So you have for Llama 2, for example, 70B, which is quite old now, but the example still stands. You have, parameters, which are usually called weights. And for the Llama 270B, they hold about 140 gigabytes. And that's what you train basically when you're training a large language model. You're tweaking all the parameters of the model until you're like happy and until you have good results. So that's when you have like some evaluation. And then you're going to do that for a long time. And how you train it, it's about 500 lines of C code usually, where, you're going to define the architecture, and then you define, the different layers that you have. In the end, you're going to have some blob. You can either run it locally, which is what we'll do today, or you can also have it hosted somewhere if you have very large language models. It can be like, for example, ChatGPT. How do you train it? You basically take the whole internet, which is about 10 terabytes of text. But then obviously you have to clean it. It's not only, just taking the whole internet and then be happy. You have to clean a lot of things. There's a lot of pre-processing that is working that you have to do. You also have to remove some specific websites, so on and so forth. But then once you have your good chunk of the internet, you're going to put it through a training, which we call. And then for Llama 2, it was 6,000 GPUs for 12 days, which cost about $2 million. Nowadays, the models are way bigger. You need way longer to train them, but the idea is still the same. You have a bit of the internet, and you're going to put through some GPUs. In the end, you get a file that is about, for this one, 140 gigabytes, and this is your LLM. And to train an assistant, you have to do, what is called supervised fine-tuning, or SFT. And this is usually what people think of when we say, oh, you have an LLM. They imagine the assistants that you have in ChatGPT, that you have in all the other models that have been released since then. But how do you do that? Actually, you have to do it with the people, with like, good old people, where you're going to create some conversations. And those are created in a way that the user is asking a question, and then you simulate an answer that the assistant would give. And then you create, in our case here, 100,000 conversations. So then you fine tune the LLM on those. And then the LLM is able to understand your questions and help you in a way that an assistant would. If you don't do that, the LLMs will not be able to actually help you. There's been, research lately, and like DeepSeek, for example, made a lot of noise because they didn't use this technique, but that's still the technique that is used by most LLMs nowadays. So let's say you want to train your own assistant. It's possible. You're just gonna need a bit of time and money. But the first part is pre-training. So yeah, you download the whole internet. You get a cluster of 6,000 GPUs. Very easy. You compress everything into a neural network, you pay $2 million, and then boom, you have your base model. But then you have to do the fine tuning. This is the one I mentioned before, where you're gonna write the labeling instructions. Then you're gonna hire people, collect about 100,000 high quality Q&A responses and all comparisons. You fine tune that, takes about a day, and then you have an assisted model. Then you're gonna run a lot of evaluations. You're gonna run it on a lot of benchmarks, and if you're happy, you're gonna deploy it. Then you have to monitor, make sure that everything's correct. Maybe you're going to correct some misbehaviors, and then you go back to step one. You're going to write some labeling instructions, etc., etc. And that's the kind of thing that LLM models do. That's why you also see a lot of new releases from the models, because they actually have to, tweak the fine tuning. But yeah, now we have an idea of LLMs. Maybe you can follow with a quick intro about vector search and vector database, how it works exactly. So vectors, why is it so popular? Why everyone is talking about them. The main reason is that it basically unlocks unstructured data. So unstructured data is, things like images, videos, documents, audio, or user-generated data. And what happens is that then you put that through an ML model, so a machine learning model, and then at the end, you're gonna get the vector embeddings. And how does it work here exactly? For the ML model, what you're going to do is that you will have a deep learning model. And usually they are trained, to give a prediction. Maybe, oh, yes, there's a picture of a cat on this picture. So they're trained, maybe to recognize something. And what you're doing is that you take the whole deep learning model, but you're going to cut off at the last layer. And why are you doing that? Why the last layer and not the first one or the second one? The reason is that the last layer has all the information that the model has learned. So that's why you're cutting off there. And why the last layer and not the last parts? Because the last part is where you do the softmax. This is where you make the prediction. So you just don't want the prediction, but you want everything. So that's why you go there. And then yes, after that you get vector embeddings. It's a fancy name, but just for list or float. And you store those in your vector database, and then you can perform search. So for search, when you can perform it, you can do retrieval-augmented generation, which is what we'll talk about today. But the thing also of like recommender systems, it's also a thing you can do. Or you can search, similar text, images, or audio. We have a lot of customers using image search, for example. And then image drug discovery, and anomaly detection are also possible. And how does it work then? How do you do the comparison? Well, in this example, you can imagine it's a 3D example. In real life, you have way more dimensions. You can think of like, 256, 512, 1024, depends on your embedding models. But then what's going to happen is that you're going to store things that are semantically similar close to each other. So if we have a look here, we can see there's a picture of a banana, and then there's the text actually banana, and we can see that they're close together. They are like about in the same space. And then if we have apple, actually the image of the apple, and the text also fairly close to the banana, but you can also have something like the company Apple is also can be like close-ish, but also not too close because it's not a fruit. So then that's the kind of thing, where embedding models are very good at. It's actually, to find the distinctions between those, being like, okay, the company Apple, yes, it's the same name, but the context where I've seen it is a bit different. So then it's projected somewhere else. And yes, that's basically what you have. Then you do similarity in this whole space. So yes, way more than 3 dimensions, but that's where you get an idea. And you can have to imagine that here, all the blue points that you see are also other vectors. They're just random vectors that we have because we have to fill this space. And yeah, vectors are just more than just text and images. So they can be, also proteins. They can be, graphs if you want to. They can be audio. They can be like a lot of things. What you need is a deep learning model that's been trained on whatever you're processing. So if you're going to work with images, you have to have a deep learning model that's been trained on images, not on text. Otherwise, it will not work. And okay, that's cool. Everything is projected now. We're here in the space, but then how do we actually run the similarity search? So we have similar graph. You have the unstructured data, transform it into the vectors. You store those in the embeddings, and then you get the embedding, sorry, and then you store them in your vector database. But then now what happens is that you have a user or yourself, the developer, you're going to run a query. So you arrive here, you're going to perform a query, be like, maybe, I don't know, I want similar images to this t-shirt that I'm wearing. I want to find new ones, you know? So you do that, you're going to transform it into vectors. Again, it's transformed into embeddings. And then here, that's where we do the magic. That's where we perform, the approximate nearest neighbor similarity search, which is a very lengthy way of saying it. We just, look for things that are similar. And then we're going to get you the result. And this is where we do the magic. That's a very optimized algorithm here. You have multiple ones to do what you want. But yes, then we're going to return you the results. And yeah, so that's why we created Milvus. Just to mention it quickly, you know what we're doing. So we are an open source vector database. And we like to say that we are easy to start. So you can just start with a pip install on your laptop. And then you can then, like insert some data and then you can run similarity search directly. And we are feature rich. So we support also like dynamic schemas, but we also support hybrid search. So meaning you can search on what is called dense embeddings, which are the numbers, and sparse embeddings, which is more like keyword search, like Elasticsearch, for example. So we support both at the same time. We also support disk-based indexing. If you want to have good results, something that is fast, but you don't want to store everything in memory. And then if you want to be fancy, we also support GPU search with like NVIDIA. If you want to go very, very fast, this is also something that is possible. And we're also ready to scale. We have 3 different offerings. We have, so as I said, Milvus Lite, which is the pip install, scale to about 1 million vectors. Then we have the standalone version, which is, a single Docker image, where then you have everything that is needed there. And this one scales up to about like 100 million vectors. And then we have the distributed version. This one runs on Kubernetes. It has the load balancer, it has the multi-node management, and you can also scale up and down each component independently, sorry. And this one scale up to about 100 billion vectors. And it's not just a random number that I'm throwing here. We actually have some customers that are running at 100 billion vectors. So yes, we're here from the beginning to the end, basically, no matter your scale. But let me talk about RAG now. So RAG, as said before, Retrieval-Augmented Generation, it's something that a lot of people are talking about because it's actually something very useful. But let me tell you why RAG and why is everyone talking about it. The first one, RAG versus LLM. So LLMs are trained to a certain point. They always have, a cutoff date until when they stop training. And so the knowledge of the LLM is usually out of date if you want to know something that is very recent. Maybe you want to know something that happened yesterday in your city. And then the LLM will be like, would likely tell you something actually, because they've been fine-tuned to be assistants and they will think they know, but they actually don't know. So then, yeah, the knowledge is out of date. And the LLM also cannot get you private knowledge, hopefully. So if you work for a company, maybe things are stored on a Google Drive or stored somewhere else where the LLMs don't have access to those. So it's like, oh, then how do we, have access to that? So this is why you have RAG. It allows the LLM to have access to your private data while also doing it in a secure manner, because then you can also stop the LLM having this knowledge. Can help reduce what we call hallucinations. This is when the LLM thinks it knows, but actually it doesn't. And then it's just going to write something because it's been trained actually to be an assistant. So it can help. RAG will not stop hallucinations, he will reduce them. And then it also is more transparent and it can actually interpret the results, because what happens behind the scene is that you do a vector search, and a vector search, you're the one in control, you're the one controlling the parameters, you can see the results, you can see the distance, so you can really debug it. Whereas if an LLM gives you an answer that is not correct, well, you're not going to be able to debug it. You have, for Llama 2, for example, you have billions and billions of parameters. So it's like, okay, that's cool, but I'm not going to go through 70 billion parameters. That would be quite a long one. So yes, that's why RAG is also so popular for like the past year. And then RAG against fine-tuning. Fine-tuning and RAG can actually work together usually, but fine-tuning is expensive. It can also be time-consuming, whereas RAG is just plug and play. But when they work together, they can also work like amazingly well. If you're deploying, a rack system in a domain that is quite specific, let's say, I don't know, medicine, maybe you want to fine tune your LLM to understand all the medical terms, but then you want to add a rack system on top of it, to actually have access to your private data, because it's different to talk about like medical things and then having access to the private data. So yeah, that's why it's so popular. It's because against those two, it really actually brings some benefits. And the basic idea, it's already been mentioned during the intro, but it's to force an LLM to work with your data. And then you do that by injecting it via a vector database like Milvus. The architecture is the following. This is for the basic RAG system. Now we have things like agentic RAG and things, but the idea is basically the same anyway. So you have your data that you start here, and then you're going to extract some content. And what you do here is like, I don't know, maybe your data is like PDFs or it's Markdowns or it's like, depending on the format. But what you want is you want to extract the content of it. You have a lot of different techniques. It's really also dependent on the data you have. It's dependent on the format you have. And then what's going to happen is that you're going to go through what is called chunking. And chunking consists of, it's a very fancy word for saying dividing, your content into different parts. But what you do here is like, you're either going to chunk it maybe every 100 characters or every 200 characters, or you're going to chunk it per paragraph, or you're going to chunk it per page. Everything depends on your data. It depends on your use case. There's not really one rule where it's like, oh, if you use this chunking method, then it's going to be fantastic. What's really good though, and what I usually say to people, is that if you don't understand what is coming out, sorry, of the chunking, then don't expect your LLM to understand it. If you can't understand what is it talking about, the LLM will also be confused and then will not be able to give you good results. So that's usually the rule that I say. But yes, otherwise there's not really anything that is good. It can be good to also add metadata about your chunks. For example, let's say, oh, my paragraph here is about this document. This is the title. This is the author. These can be very useful. But yes, once you have your chunks, then you're going to put them through an embedding model. And then that's when you get, all the vectors. And you're going to store it into Milvus directly. Then you are the user yourself now, and what happened is that you're going to have a query, and then you put it through the same embedding model as you used before. Rerun then a semantic search, and then that's when Milvus will return, the most similar data to your query. What happens now is that the LLM always has some context. It's usually like either the user context or what we would call prompt, but the user prompt, the system prompt, assistant prompt, they have all of those. And what's happening is that then the similar data, the result that you have, you put that in the context of the LLM. The LLM then knows, oh, okay, this question was asked by our user. Here is the results that I got from this search. Here is what I can tell about it now. And this is then how you force it and you inject it with the context for the LLM. Then produces a good response because they've been trained to be assistants. So this is the basic RAG architecture. And if you use LangChain, it is basically, it is basically 5 lines of code where you have, your vector database, and then you have your different documents, and then you're going to say, please, for those documents, use those embedding models. You're going to create then what is called query answering chain. And so then, you have your retrieval query answering, use some specific LLMs, and then, the chain type can be like a lot of different things. Usually it's going to be like, LLM, vector search, and then response, but it can be whatever you want. And you define your vector database as the retriever. So then we know, oh, before we actually answer, we check the similar data, and then we inject it. And yes, then you have your question, and then you have a basic rack system now. And yeah, I'll let it over now, Toon, for you.
Okay, so if you care about current context and you care about events that happened recently or events that are happening right now, that's the domain of real-time systems. And real-time systems are enabled by streaming data. Right, let's check if I have control. Here we go. Yeah. So let's talk about the different types of system here. So everyone's probably familiar with what a database is. You have them on your phone, you have them in your homes. And I'm talking about largely like relational database systems, or RDBMSs. And there are also analytical databases as well. And this is where the majority of data gets stored, and they're stored in these things called tables. Now, with streaming data, you've got to take a different approach. You have to build a different type of data store from the ground up. And this is the type of data store it is. It's called a message broker. And much like tables, they're stored in topics. And to explain what streaming data and real-time systems are, I kind of have to compare it to what everyone else is doing, which is batch, which is the predominant way, the predominant approach for building data systems. And it's based around the concept of processing data at rest. So you've got my database there in the middle. So in this example, we've got that cyclist at the top there, and they have a smartphone app, and a smartphone has sensors. So it's going to be transmitting certain data points over the wire, and it's going to end up in this database. So as that rider reaches different points, it's going to transmit that data, and it's going to get saved into that database. So that's one data point that's appeared. A short time later, another data point is going to be generated, and it's going to be transmitted, and it's going to end up in the database, and so forth. So that data is collected over time into this database. Sometime later, a scheduler or a scheduling system is going to kick in, and it's going to grab that data. So it's going to select all that data, and it's going to load it into a processing system. Sometimes it's the database itself is the processing system. Sometimes it's an external kind of tool. And we call this bounded data. And it's bounded, as the name would imply, because it has a start and an end. So when you select this data, you may be selecting, for example, things like, give me all the data for this cyclist in the last calendar day or in the last hour. So that has a start and an end. So you would select that, and you'd load that into the processing system. And in this case, we're interested in the gravitational forces. So we're taking that accelerometer data from that smartphone. And we've got the first column there, which is a timestamp. And then we've got the X, Y, and Z axes for the Gs, the gravitational forces. And so we've selected that data, and now we can start deriving other data from it. So one example would be like create a column for the total, where you would sum up all the X, Y, and Z. So now you have gravitational forces as a total. And then you might be interested in how those forces, the sum of those forces changes over time. So you might be interested in the delta. So you would be able to derive another column. And the point here is that that computation is happening on all that bounded historical data. Because all that data is read into memory, you don't need to maintain any sort of intermediary state. That data is just there in front of you to compute. And because you're introducing a delay, the results are not in real time. And this encapsulates like 99% of all the systems out there. Now let's compare that with streaming. It's a different approach. You're processing data that's in motion now. So you're keeping the latency low by not introducing any sort of delay. And that data is collected over time into a broker or transport. So if we take that same cyclist, they're going to generate a data point and transmit it, ends up in the message broker. Immediately, it's going to get processed. So it gets loaded in and processed as soon as that data point is generated. And we call this one unbounded data because though it has a start, it doesn't have an end. Like it's unknown how many more data points will come in. So we call that unbounded, and it is continuously consumed and processed. So if we get a second data point here from the cyclist, that will come in. And when that data point arrives, we have another data point to process. And you'll see that we're maintaining state because in between data points, you have to maintain that state. So it could be anything that you care about. In this case, since we care about the totals, we're going to keep tallying those up. So you need to maintain that state and so forth with all the data points. And the point with streaming systems is that that computation happens on each event that comes in every time. And it requires that state so that it has some semblance of what of historical like computation, that aggregating function there for the total, and you get real-time results. So there's no latency, no sort of delays, no delays are introduced. And so I created this 2-button meme for this. You're probably wondering now that I know what batch systems are and what streaming systems are. How do I design? Which one do I choose? So I created this one with 3 buttons. The answer is both. And the reason is because they are complementary. One doesn't replace the other. You need that batch data for historical context, and you need the streaming for the current context. So it's probably now making sense in the context of a RAG system. Like Stefan mentioned, the cost to generate one of these LLMs and to fine tune them I don't know about you, but I can find a better way to spend $2 million than 6,000 plus GPUs. So you want to prevent doing that repeatedly. And to do that, you have to utilize the data, that private knowledge base that you're generating and saving over time. And most teams will try to fit that streaming paradigm into a batch system. But sometimes you've just got to rethink it to get things to work optimally. I find it much easier to fit batch into a streaming system. And to do that, you have to start thinking about the events, those data points that are generated. Those are the foundational units of your system. And you may have heard of things like event-driven programming, event-driven systems. And this is kind of what we're talking about here. So the kind of streaming data use cases it enables, many. So I'll go through a few here. So in financial services, fraud detection is a very popular one. If you've ever been on holiday, I think it doesn't happen as well now, as much now, because the machine learning models are so much better. But there was a time when you would go on holiday and you would pay for something in a shop and you would get an SMS from your bank telling you that we've detected this, was this you? Glad that doesn't happen much anymore because of machine learning. But this is the sort of thing that's a real-time system. It would be impossible if it wasn't a real-time system. It's also used in algorithmic trading and things like risk assessment. So an LLM here would be fantastic for trying to detect fraud based on data points, and also for a risk assessment, like generating a score from a series of events. Moving on to retail, e-commerce, and customer service, I think LLMs have been utilized the most as chatbots. So you can imagine building real-time systems around that, where a user is maybe navigating a shop in real time, and maybe they'll want to chat to a chatbot, an assistant, and that assistant will have knowledge of what that person was doing in that session and be able to upsell or provide discount coupons for, that t-shirt you've been staring at like for the last 5 minutes, that sort of thing. So it's great for recommender systems. Physical items take up space, and that has a cost. So inventory management, being able to optimize that using real-time data is also really cool. And lastly, manufacturing, energy, and industrial IoT. So all these factories and plants that generate energy, create batteries, machinery, and products. They all have these robots. All these robots have sensors, and those sensors enable you to monitor the conditions there. So a common use case there is predictive maintenance, where you take that current data, and the most straightforward way to do this is measuring things like vibration and temperature. And when you start detecting anomalies in that, you can understand that this machine is probably going to start failing very soon. So this has like real good implications around operational efficiency and worker safety. So very important use cases there. You're probably wondering why streaming so fast. In this case, we're going to talk about Apache Kafka, which is the system that is the most predominant one out there that everyone builds against. The first thing is sequential I/O. So if you see that random I/O diagram on the left, that's generally how databases store those data points. It's kind of, with databases, they're general purpose. You tend to query across like random ranges. You have all sorts of queries. So the data being interspersed like that, it makes sense. That's how it will write that data. But with Kafka and message brokers and real-time data, you tend to read things kind of in sequence as they're happening. So you need to store events that occurred close in time and are related to each other, next to each other. So because they're in contiguous blocks, you're able to read that data in really quickly. So this has really good implications around modern drives, such as solid state drives, because that's just how they love to work. And so you get all these speed increases. And the second reason is this concept called zero copy principle. So that data has to pass through different representations between the kernel and the actual application memory. So there are different representations, and that has implications around utilizing CPU to do that. But with Kafka, you're able to read directly that data. It's called direct memory access with very little or no CPU involved. So it's extremely fast. And I'll talk about Quick Streams next, which is the open source Python library. So a bit about the background. So Kafka was designed by engineers at LinkedIn about 15 years ago. And it was designed to solve all these huge scale big data, real-time and data distribution problems at LinkedIn. And a lot of that was written in a language called Java. So everyone programmed in Java, and that has been how the landscape has been shaped for real-time and streaming data. But in the last few years, what we've all noticed is that the new wave of data engineer and data practitioner learns Python or learns Python in school. And as a result, over the years, you've got this rich ecosystem of different types of data tools across many different industries. So Python has so many different algorithms you can get out of the box, different types of tooling. And for that reason, it made sense to try to build something using Python. And that's why QuickStreams was born. It's a pure Python library, and pure Python in this case is really important because a lot of other frameworks will take that Java and put a Python wrapper around it. That's not great for developer experience because when you are building systems, you kind of iterate your way through and you fix bugs, and it's not very helpful when the bugs are in another language. So you get everything in Python, you get the line number where the error was, so it's a really good experience. There's an open source sources and syncs API. So we've got a few sources and syncs ready to go. But if you wanted to connect to other database systems in your company, if you wanted to access like third-party vendor data systems, you're able to build that out. We give you a framework that enables you to give you a lot of good things for free, like retries, back pressure, things like that. So it manages all of that for you. And because it's built on Apache Kafka, you've got all the fault tolerance and that scalability. It gives you access to these high level abstractions like stateful window operations and custom aggregations that you can build. But one of the defining characteristics of QuickStreams is that you process data as tabular data using streaming data frames. And you may be familiar with other types of data frames. There's other libraries like Dask and Pandas that use data frames. And what they do is they give you access to records in a tabular fashion. So here in QuickStreams, you're taking those messages and you're making them table-like. So you're able to access the data as columns. And here's kind of how it looks. So it's quite a succinct way of programming. You import in QuickStreams, you create an application object which connects to your Kafka broker. In this case, it's running locally on port 9092. You define an input topic that you're reading from and an output topic that you're going to write to. So you can chain it all together and build a data pipeline. And from that, you'll see that we create a streaming data frame from that input topic. So every new message or every new record that comes into that topic, you're going to apply this function. And here we're just deriving and creating a field C by summing field A and B. But you can do absolutely anything. And you can see that it's being accessed through the columns there. So if you're familiar with pandas and other data frame libraries, this should be very intuitive for you. And that app.run, so with streaming data, because it's continuously updating, continuously checking to see if new messages have arrived in that topic, it runs in kind of like an infinite loop. So it will be a continuously running application. And I'll just go through a few other examples. So we've got a stateful function. So you have access to this high level state object, which is like a dictionary, and you're able to save that, and that will get persisted in between event invocations. And then you have stateful window operations. So we support tumbling windows, hopping windows, sliding windows. And this enables you to figure out things in a kind of discrete chunk of time as time passes. So this is extremely useful for things like predictive maintenance, where you're trying to detect certain anomalies in a given time period. And yeah, back to you, Stefan, for real-time RAG.
Oops, sorry, I clicked somewhere else, but yeah, thank you. Yeah, so real-time RAG, well, as it's written here, is to make sure your system has access to the latest data. So what we've seen before, when you have a topic that you're listening to all the time, then you also want to be able maybe to query it with a RAG system. You don't want to process everything per batch. So yes, that's what we built. Let me go here. And for the tech stack, what we have is we went with LangChain. It's a classic open source framework for building LLM applications. It's likely you've heard about it. It's extremely popular and it's quite easy to start with. They have a really insane amount of documentation to help you start with anything. So it's very, very useful. And they're focused on retrieving data and integrating with LLMs. So this can go from, vector database like us, but also it can be, I don't know, the internet, or it can be anything related to just retrieving some data somewhere. And they have integration with the most popular AI tools. Then for the model, we're going to run locally Mistral 7B. This one is very good for fast response and low latency as well function calling. And it runs, it can also run on MacBooks with 16 gigabytes of RAM, which you quantize it. So this is very useful. And for that, we're going to run it with Olama, which is one of my favorite tools in the open source world. They also have very cute stickers, as you can see here on the right side. But they basically allow you to run LLMs very easily. They support basically every open source LLM there is, and they make fantastic work. So have a look at them. Then we'll use Milvus for the vector database. So I've mentioned it already, but yes, this is the one we will use. And we also use Quickstream that you can, that was mentioned, sorry, before. And yes, let's go into the demo. So first, just let me zoom fully in. Just so you know, everything's running on my laptop at the moment, and everything is running through Docker. So I have the different services for Milvus that are running. So etcd for metadata, MinIO for storing the vectors and everything, and then we have Milvus here that is running actually the computation and the similarity search. And then we have Kafka running here as well. So we have the broker and we have everything related to Kafka that is running. So yes, everything is running on my laptop. There's nothing, there's going to be no API calls anywhere. But this is what we have. So yeah, as I've said, LangChain for kind of the orchestration and everything, Quix for the data streaming and real-time updates, Milvus for the data storage and the vectors, and Olama for like model execution and processing everything locally. So the idea of this notebook, sorry, is to build a rack system, but one that can, answer a question using Milvus, that can also use it with Quickstream, and that can update its knowledge in real time. So yeah, we have LangChain, Milvus, Orama, Quickstream, and Apache Kafka. So let me make sure, I don't lie to you. I'm going to restart the kernel. So we have like everything's from scratch. Let me run the import. Perfect. And now what we're going to do is that we're going to start the different RAG components. So for this one, I'm using a very simple embedding models. This one is very, very small. It's trained on English. So this is a good one. It's on Hugging Face. People usually ask me, where do you find the embeddings? Hugging Face can be a very good resource. They have leaderboards, for the open and closed source ones. Just as a reminder, don't pick one that is the first one. Pick one that is good for your use case. If you work, I live in Germany. I work with German data. Most of the embedding models are trained on English, so then they wouldn't be as good. So just have a look here. But for this one, it's a simple use case. We're going for a simple embedding. Then I'm using Olama here, which is running on my laptop. And I'm saying, okay, I'm going to use the Mistral model, which is the 7B. I'm just going to start Milvus with actually just one document here, which is an empty document. And then I just define, okay, the name of the collection. And also, so I don't, make sure like everything is running from scratch, I'm also going to drop the old collection if it exists. This is the prompt that we're defining, the template kind of for the rack system. So it's like, okay, answer the question based on the following context, and the context is the the return from Milvus, and then the question is the question from our user directly, and then we have the answer. The answer will be generated by the LLM. So yes, we're gonna create this prompt then from this template that we have, and then you create a chain. So this is what I mentioned before, where you're the one defining it. So for us, we're gonna have the context, which is the vector store, and the question, which is gonna be for my user, and then we're gonna be like, okay, first the prompt, then the LLM, and then we're gonna output the parser. We're gonna use an output parser, sorry, to output it as a string to make sure that it's like it's like natural language, then it's string. You could also use maybe a JSON output parser as well if you want to return it in JSON or different components. But yes, let's go. We're gonna set it up. So now what happens is that we're creating the rack collection, we're inserting the document in Milvus, and then we created the rack template. So we can, have a look. And for like our initial rack system, we're gonna have, the question that is here, which is, what do you know about artificial intelligence development? Hopefully, the model will not hallucinate, and then it will actually give us an answer that is like, oh, I have no idea, because as you've seen, we just inserted an empty document. So let's have a look. So we have the question. Yes, cool. So really, it's like it provided the context. So the context is the mirror search, and then it's like, okay, based on the provided context, actually, I have no idea. And this is how then you can, force your LLM kind of to also work with your data. And then if it doesn't know, it's also possible that the LLM will be like, actually, I don't know. Then we're going to move on more to the Kafka part. So here I'm just, gonna clean up the topic just to make sure as well that, again, like we're proving that everything's from scratch. So we're just, deleting the topic with different messages. And yeah, I'll let you take over here from.
Yeah, so now that you've got a clean Kafka setup with like the topic that's been dropped, you're going to import in quick streams and you're going to construct this sample messages. So what's the current context that we want to answer? So the question was around artificial intelligence and around climate change. So we've set in these messages that we're going to send through into Kafka. So we're going to produce these messages to Kafka. So first of all, you're going to create an application object and you're going to connect to the local Kafka that is running in Stefan's Docker Compose. And we're going to auto create the topics because we just dropped it. And then you're going to get the producer out of the app and you're going to just send those messages. So you'll notice there that there's a topic called messages. And then you've got a key there as well. A key is not completely important in this context, but a key enables you to read these messages out in order. So we want to read all of chat ID 1's messages in order. So we're keying it on the chat ID itself. And we're going to save the text in and we're going to process that later. So we're going to run this. We're going to send all these messages in. So now they're in the Kafka topic. And then now we're going to move on to processing that data. So in the same way, we're going to create an application object. Consumer groups there, you'll see, are how you scale out Kafka writing and Kafka reading. So not important here, but we're going to define something there. And since we're initializing this for the first time, we want to read from the earliest point in time. So we pick up all the messages. In some cases, you would set this to latest, but here from scratch, we're going to set that to earliest. And we're going to define the topic, which is called messages. That's where we previously produced the messages to. And then next, we're going to create a streaming data frame. So this is going to create data frames on the fly. So every new message that it reads will be sent in 4. They're going to be represented one at a time as a data frame. And then next, we're going to run the apply function and pass in that process value. And in that function, process value, all we're doing is we're extracting the text out of that record. We're printing it to the console so that we can see it. And we're adding it to the vector store. So it's going to go through the whole the whole embedding step and be saved in Milvus. And then we're going to do an app.run, and it's going to run in a continuous loop, which isn't great in a notebook, but in a live system, it's fantastic. So if you run that, it's going to process those messages. We're going to see those logs, of course. And under the hood, it's been saving it into Milvus. So yeah, we can interrupt it and then.
Oh, yeah. Yeah, stopped it now. So you can see.
Great. And then, onto the updated RAG system.
Yes. And now, so yeah, I said everything should be in Milvus. So now we can actually ask different questions, like one about AI developments and then one about climate change. And then now we can see, okay, we're processing it. And now we can see, okay, the latest developments in artificial intelligence have revolutionized how we approach problem solving. This is, what we put here actually. And then the LLM thought it was good. So it just actually produced it. And then we can do the same for the climate change. And then we can see, okay, now it's like, according to the provided context, climate change poses, significant challenges because this is what's rewrote here. And then you can actually see that LLMs will also, depending on the way they want to answer, depending on what is activated, actually, they might give you different answers. So you see this one is just basically the result of the vector search. This one is like, okay, I'm going to help you a bit with the provided context. But yes, this is then how you can, use RAG streaming, build a RAG system. And just to continue, if you want to do it in prod, then for us, there is Zilliz Cloud, which is basically Milvus behind the scene. Then there's Quix Cloud as well for streaming apps and pipeline. Let me know if you want to add things here. But then otherwise, for the inference service, you have either you can use the APIs directly. Otherwise, if you want to do it yourself, highly recommend checking out VLLMs. This is a tool to host LLMs, and it's actually usually provided by all the providers. Basically, they always offer it, and then you can host your model yourself, making it possible for you to then control the model, and yeah, have more control over your LLM. And yeah, thank you. That was Stefan on my end. And I had Tune as well. And I guess we'll take questions from here.
Yes, thank you very much, everyone.
Great. Thank you both very much for that in-depth presentation. We've got quite a lot of questions coming in with just over 10 minutes to get through them, so hopefully we can get through as many as we can. A couple of people have asked similar questions around if you have any recommendations for resources or online courses where people can read a little bit more about the techniques that you've discussed. In particular, working with Brags from scratch, and also Shalina in the chat has asked if there's any kind of step-by-step guides that you might be able to recommend for how to kind of put this into practice.
Mm-hmm. Maybe I take this one. I write a lot of blogs actually about that, so you can check directly our blog post. Maybe I share it in the chat if you don't mind. I'll share it with everyone, but it's zelis.com/blogs, I think. I think it's /blogs, so I have to check if it's /blog or blogs. It's blog. Okay. But yeah, that's one where I actually write a lot about RAG and, like with using different models as well, using different tools. There's also like a lot of, actually fully guide, like one step by step. So that can also be very useful, I would say.
Yeah, I think it's great to always follow a guide and just like kind of like search around for the other bits. So we've thrown quite a few technologies there, like Jupyter Notebooks is something that we take for granted and use all the time, but we understand someone may be new to that. But like having notebooks is such a really like clear way of being able to learn as well.
Mm-hmm.
And you pair that with Docker Compose, which lets you run these containers on your machine so that you can do everything offline. Like you don't have to do these like network calls or use like an external provider. That's what it's all about. So yeah.
Brilliant, thank you. And a similar question, but a bit more specific from Terry Francis is asking if you could either explain it a little bit more or maybe provide a reference for finding some more information about reducing the size of an LLM for applications of IoT and smaller edge intelligence devices.
Yeah. So there are different steps for this one. You can either quantize the model or you can distill a model. So quantize is actually, like changing, like if you go from, for example, for floating floats to int, then you can reduce the size of the model in memory. You can reduce it by like half if you go from FP16 to FP8, even more if you go into ints. What's going to happen though is that you're going to lose some precision. So there's always a trade-off. Then another one, which is a bit harder, it's called distillation. Distillation is taking a smaller model and then train it on the answers of a bigger model. So then it kind of learns, it's like kind of like teacher student. And that way you can also like use a smaller model and then deploy it. Then otherwise for really specific on the edge, I know Mistral actually has two, what they call like Ministral, which are like they're actually made to be run on edge. So have a look at those. I think there's like 1 billion parameter, for example, and then it's actually made for it. So 1 billion, FP16 is 2 gigabytes of RAM. FP8 is actually 1 gigabyte of RAM. So it can be very good.
And our customers, industrial IoT, which is the use case you mentioned, like if you're not already downsampling, you probably want to do that as well, just so you can take the signals that you care about. So that will help further reduce.
Brilliant, thank you. And then we've got Surya who's asking, is RAG plus your choice of model by itself enough to prevent hallucinations, or are there other strategies that you would consider?
There are different strategies. So it's going to reduce them, but then it's also going to depend on the power of your RAG, basically, if I may say. So it depends on how you do it. I've shown basic RAG systems, which are good, but they can also, they might not be help you if you're looking for something like that is brand specific. Let's say you're like an e-commerce website and you're looking to search for like Adidas shoes. Well, if you run a vector search for the vector store, Adidas and Puma are very close together. So then, they might not be able to understand that. What you want to add on top is keyword search, actually. So then that's what you have, what is called hybrid search. And that actually is the one that will like really help you, because then it will be like, oh, you're looking for Adidas shoes and you want Adidas shoes, not the rest. So then, this would be picked up. And then you have things. So yeah, that can really, really help you as well.
Brilliant, thank you. And then we've got Ollie is asking, Ollie is studying machine learning currently, but is interested in working in healthcare in the future. Is healthcare an area where you could see this working well? And have you seen RAG used in healthcare? Or are there other more appropriate tools that would be better suited to healthcare?
Twin, maybe have you worked in the healthcare field a bit?
Yeah, I have. Like the kind of the use cases, I think with LLMs and generative AI, there's a lot of work around putting guardrails in place. And generally, putting guardrails in place means putting a human in the loop. So having a lot of the queries answered in real time with certain caveats, but putting it through a different workflow that enables a human to look at the generated output. I think healthcare is an interesting one. Like you should always speak to a human doctor, not a facsimile of a human doctor who will just answer any question you throw at it, whether they know the answer or not. So definitely in healthcare, you got to be a bit more careful, and that's where a lot of this research around ethics and guardrails have been put in place.
Yeah,
so it's still early days, right?
Exactly, and I've seen. I think I don't remember the name of the company, but they just raised a huge fund. Actually, they're specialized for RAG in healthcare. So it really depends. Depends what you want. If it's more like drug discovery and things can also be useful. Depends on. Yeah, as Toon said, if you're like talking to the human that is sick, or if it's more like a bit more in the back end doing research.
Yeah, but for things like drug design, things like that, yeah, finding patterns, machine learning models are great at that. LLMs interpreting them, yeah. If the LLM was trained on this sort of data, and there's no doubt there are plenty of those. I think a lot of them aren't free foundational models, though, are they, Stefan? I think like a lot
No.
of those are private, and a lot
Yes.
of the pharma companies are building that knowledge up and spending millions of dollars doing it themselves.
Brilliant, thank you. So moving on, we've got Iman is asking. I think this question came in quite towards the beginning of your presentation. I think it was when you were discussing LLMs. What is the cost of the fine tuning that should be done each week? If you have any figures.
I think it's like it depends on what you're using, but it's going to be like a couple of hundred of thousand, or like tens of thousands of dollars. I guess now it's more couple of hundred thousand of dollars that they're doing. But yes, that's kind of the cost. So it's still cheaper, but that's why you only have few companies doing also foundational models.
And then we've got Craig asking, how do RAGs handle conflicting or outdated information? Do you need to retrain them if the source data changes?
So this is a very good one. The way to do it is actually to use metadata. So the way I usually advise people is don't just put your text or your chunk, actually add information about it, to also help you. That's the way it's outdated. It's likely because you've seen the date in the metadata. So add that as well. And then when you do the search, you can also add some filters, maybe be like, hey, let's do that. Or then you return it. And then the LLM will see, oh, it's from 2015. This is quite old. And then it will tell you as well. So like use those, return those to the LLM. It should work.
Brilliant. And we've discussed healthcare, I guess. Lisa's asking, are there any other industries where you see RAG being of particular benefit? You'd mentioned manufacturing as an example, too. Are there any others where you think that RAG would be really beneficial? And also, what do you see as its kind of biggest limitations?
To me, it's customer support.
Yeah, I think customer support chatbots, right? I think we've all encountered them at this point. So yeah, any sort of like facsimile of a human agent, basically, that's where the future's heading. Yeah, I would say, like, to be honest, like a lot of the industry, like everyone's, like lots of different industries, different companies have R&D budget that they're committing towards generative AI. So I think, like, even though it's been happening for the last 2 years, seeing some useful applications, they're coming out. The main kind of use case I see is taking data and having the LLM interpret it. So when you use a RAG system that gives it further context, you'll be able to then define. So for example, if you've got loads of data in a table, you could have the LLM try to interpret that, but it may not understand concepts such as churn and retention and these kind of like business terms. But if you can provide that context and something specific to your business, then it's going to be able to function correctly. So I can think of kind of like augmenting like the kind of like local and like private knowledge that you have and the concepts that you use in your business to the general LLM, and you'll get better results. So yeah, it's untold, but yeah, we're seeing it's an interesting area to be in because there's loads of different things happening at the moment.
Brilliant. Well, thank you both very much for joining us this afternoon. It's been really interesting. We've had loads of questions, so I think the audience have really got a lot from this as well. You both have got your or you had your LinkedIn's, I think, at the beginning of the session. So if people want to get in touch, are you happy for people to send you a message?
Yes, please do so.
Absolutely. And there was a question about the slides and like the repo as well. So yeah, we can share those too.
Yes.
You can run this yourself.
We recorded the session as well, so we'll make the recording available for anybody who's come along. So if you've registered or you're here today, then we'll send you an email afterwards with a link to the recording. We just had one last question coming in last minute there from Terry, just asking how any recommendations for how to get into this area of work?
Well, it depends, but to me, it's like the way I advise is like build something that you're like interested in that annoys you. So like maybe based in Germany, we process a lot of things with mail and like physical documents. So I have like a whole rack system where I take a picture of it, throw it at my LLM, and then I can answer questions. That's the way I started as like, okay, I want to learn more about this, and then while you do that, then you're like, okay, at first my results are not good. How can I improve those? And while you need something that you care about, I feel like it's just way better to learn than just following a tutorial. So yes, that would be my advice.
Yeah, that's the best way. Best products are built scratching an itch, right? So
yeah,
yeah, lots of young folks straight out of university starting their own companies. There's a lot of venture capital and funding in Europe, especially. You may have seen the news about how much is being committed to spending on AI in the EU. So yeah, there's lots of opportunities about to be formed.
So basically, find the problem that annoys you and figure out how to fix it.
Yes. Hopefully, a lot of other people have the same problem, and they're willing to pay to make it go away. That's the short answer, right?
And then we've got 1 minute left. Just a last minute question came in from Imana there. Can we use annotated corpus as RAG?
Not sure to understand this one, but depends on what you mean with annotated corpus, to be honest.
Iman, maybe if you want to get in touch with a bit more context to your question.
The corpus we use for training. Well, it's not really the same. So for training the model, it's basically the whole internet. So you wouldn't, use that. For RAG, it's more like you have your private data that you give back to the context, to the LLM.
Okay, cool. Well, thank you both again for joining us. We will, as I said, we'll share the recording with everybody afterwards. If you are happy to share your slides, I can also send them out to anybody who's interested. And yeah, just again, if you're not already a member of the community, please do join. We've got loads of webinars and events coming up. We run in-person events each month as well. We've got Data Fest coming up, which is our flagship conference in May. So if you want to get involved, you can join for free. Get in touch if you've got any questions, and hopefully we'll see you at the next one. Thank you.
Thank you.
Thanks so much. Bye-bye.